Hey everybody, it's Ripley back again. We're going to talk a little bit about calculus of parametric equations. So we already spoke about the being able to find the length of an arc carved out by a parametric equation. So like, if I've got t equals a and t equals b, I know that the arc length is equal to the integral from a to b of the square root. If this guy, by the way, is defined by x of t, y of t, right? So I've got, that's how this is our function, right? That's how this thing's defined. Then this would just be x primed of t squared plus y primed of t squared dt. That was from last section, easy. But what if I wanted to figure out the equation of a line tangent? So that's a little trickier. And I don't want to figure out the equation of the line tangent right here at some point. Let's go x of t naught, y of t naught. But I'd like to be able to figure it out in Cartesian coordinates, in standard issue x f of x coordinates. I guess that's a better way of putting it, isn't it? So how do I do that? Well, it's actually pretty easy. I'll show you how. So if I've got, I know that slope is equal to what? Well, I know that slope at any point is dy over dx, right? We take, if we had a function of x, we would just take the derivative and we would plug in an x value. However, how do we incorporate the fact that this is a parametric equation? I have to have something that's got a t in it. Well, that's pretty easy, right? All I got to do, this is the coolest part, is dy over dt over dx over dt, right? Now this would be to evaluate this, I would just put t at t naught for this guy, and t at t naught here. Now, if I want the equation of a line, I would simply find y of t naught, y minus y of t naught, just by using point slope, which we love, y minus y of t naught, jeez, I'm a mess, is equal to m times x minus x of t naught. So let me do a quick little example for you. This section does not take long at all. Let's suppose that a curve is defined by x is equal to t squared and y is equal to t cubed minus 3t. All right? And I want to figure out let's find the equation of line tangent at, I'm going to go 1 comma negative 2. That's what I'm going to do. At the point 1 comma negative 2. Now I got to be a little bit careful here. All right, what do we need? Well, we need a slope and we need a point. Oops, we need a slope, that's supposed to be a colon, and we need a point. So a slope m and a point xy. Well, I've got what x and y are equal to. However, these are in terms of t, aren't they? This ostensibly is 1 comma negative 2 at some point down here. I could graph this and look at it if I wanted to. In fact, maybe we'll do that afterwards and see if it makes sense. We'll graph this and then we'll look at the equation of the line as well and see what it does. All right, so first thing I need to do, if I'm going to make these work, right, because I got to use them in here, is I got to figure out a t value that corresponds to the point 1 comma negative 2. Well, how do I do that? I can take t squared is equal to 1. That implies that t is equal to plus and minus 1. Okay, that's cool. I'm not afraid. And then I have to do what? Let's see. Y, I've got negative 2 is equal to t cubed minus 3t. Now, 3t, not 3, 2. 2 for t. Oh, did I really just do that? That's awful. Now, the way that I do this is I know that by x, t squared equals 1, so t can be plus or minus 1. I'm going to plug these in and see if I get I'm going to plug t equals 1 in and see if I get negative 2. And then I'm going to plug t equals negative 1 in and see if I get t is equal to negative 2. So let's look. Plug 1 in. I get 1 minus 3, negative 2. Awesome. So I know for sure that t equals 1 is a solution. How about negative 1? I get negative 1 plus 3. Crap, that's 2. So t equals negative 1 does not work. Well, that's nice. That just means only one of them works. Now, you may ask me, Ripley, what happens if they both worked? Well, that would imply that we had some sort of curve that went, let's put down here at 2 comma, or 1 comma negative 2. It would imply that we had a curve that went something like this, and then maybe it curved back on itself, like that. So I would have one equation of a line tangent in this direction, aha, and then another one, sham, in that direction, which is pretty cool. You may say, well, how many can I have? I guess you could probably have an infinite number, couldn't you? Because if this thing just kept dialing back in on that thing, almost like a weird sine or cosine parametric curve, you could have an infinite number of those bad boys. Theoretically, you could build one such that was the case. If not, disregard what I just said. I guess, well, let me think about that. I think I could get an uncountably infinite number. I know I can get an infinite number, but it'd be a pain in the butt. I'm digressing. All right, let's go back. Let's get to this color. I know that m is equal to dy over dt over dx over dt, which in this case, well, dy over dt is going to be 3t squared minus 3 over 2t. Now, where am I evaluating these at? Because it doesn't make any sense to plug in 1, negative 2. We know that we're playing at t equals 1. So I can go, you know what, I'm going to be lazy and just go vertical line, t equals 1. And I'm going to erase this guy right here. So what do we end up with? Oh, that's interesting. It's going to be horizontal, isn't it? So m is going to equal 3 minus 3 over 2, excuse me, which is equal to 0. So I've got a horizontal line. So what's that mean? What does y equal? Well, remember, the hard part about this is that you're jumping back and forth between rectangular coordinates and parametric ones, like functional coordinates and parametric ones. I don't know if I'm saying that right, but I think you understand what I mean. That implies that the equation of my line tangent is going to be y equals negative 2, right? Makes sense, doesn't it? Now, let's graph it just for giggles, just to see what this thing looks like. All right, let's go. I want to go into over here and grab my TI. I probably should have had this open, but I didn't think that I was going to do it. All right, I got t squared, and I have t cubed minus 3t. Let's go y equals, and we'll clear this thing. Whoa, close that thing. Clear this thing. Clear, go away. And we're going to go to, remember I got to go to mode, and I'm going to go to polar, so I got to crank down a little bit here, sorry. This is good practice for jumping in and out of modes. All right, hit enter, go back here, and then I'm going to go to y equals, I'm going to go clear, and I'm going to go, what was it? It was t squared, right? Whoa, did I go to polar? What the heck is going on here? Oh, I did. What a dangus. Sorry, you guys. Let's go back here. I should edit that out, but I'm being lazy. Y equals, oh, good lordy. Let's clear that. Clear that. Oh, wow, you guys, I'm sorry. You're going to have to deal with me clearing this out here for a minute. I wonder why I did that. I don't recall doing any of this. All right, almost done, I think. Okay, done. Oh, nope, clear. And up we go. Sorry about that. Oh, good Lord. Oh, come on. Sorry. Bear with. I don't know. Did somebody hack into my clear? Sweet. Goodness. Can I go just down? Nope. All right, try it again. I apologize. So we're doing t squared and t cubed minus 3t. So t squared, t, whoops, squared. And then for y of t, we're going to do t cubed minus 3t. This is going to be t cubed, and then minus 3 and t. Let's check our window real quick. It's in the standard. That's kind of weird. We might want to go, let's go t min between negative 10 and t max to 10, because we're not talking about trigs here, are we? And then let's go zoom and go zoom standard, which is 6. And we'll just, whoa, look at that thing. Wow, that's crazy. So over here at 1 comma negative 2, it does appear as though my line tangent is horizontal. Now, can you think of how to do a quick line of y equals negative 2? It's pretty easy, right? You just let x equal t, and then you let y equal negative 2, and then graph it. Look at that. Yeah, there you go. That's pretty sweet. Okay. Now, wait a second. What's my window again? I went negative 2. Oh, I didn't do my y. Let's go y. Maybe it might get interesting. Let's go. Y max is 9, max is 10. Okay, cool. I guess that'll do. Let's go back to the graph. Sorry, you guys. So any other point along here, basically, I would use exactly the same technique, and I would end up with the line tangent to it. It's beautiful, right? It wouldn't be as pretty as y equals negative 2, but it'd still be pretty pretty. It's like me. I'm not real pretty, but I'm pretty pretty. I'm an idiot. Okay, now I got a question for you. Let's say that we have a curve. This is kind of fun. Let's say that we have a curve that's defined by a parametric equation. All right, so we got x of t and we got y of t, and that's describing this guy. And I want to take the integral between a and b, right? All right, so I want to find, we know, now you may say, but Ripley, this is already a function. Well, yeah, it is, but it might be hard to identify what function it is, right? So let me show you a trick. There's kind of a neat little trick here. The integral from a to b of f of x dx could be written, if we wanted it to be written, as y dx. Do you agree with that? That's pretty easy. Now, just to make ourselves not, I'm going to, because this can get pretty confusing, I'm going to let x of t equal f of t. So x equals f of t. In other words, x equals f. And I'm going to let y equal g of t. All right? Now, if you think about that, another way that I could write this, if I want to turn it into parametrics, I could simply say the integral. We'll worry about the limits here for just a sec, because you've got to be real careful with the limits, right? I'm going to take the integral. I know that y is g of t, and then if I want dx, I just use a differential. In other words, if x equals, if x equals f of t, then dx is equal to f primed of t dt, is it not? So I've got times f primed of t dt. Now the question is, what are my limits? Are my limits from a to b? Well, no, because those limits are on x, right? This is the x-axis, this is the y-axis, and we're putting this parametric curve over the top of it. So what we're going to do is we're going to correspond to some, we're going to say t naught. I guess that's kind of bad form. I think the book uses alpha, and then t1, and we'll call this thing beta. So now I have to find the t values that correspond to the initial point and to the final point. So that would be alpha and beta. That's the biggest trick, is remembering that these limits are limits on x, and what we need are limits on t, which can be difficult to visualize because you're like, wait, where does t live? Well, t doesn't live anywhere on the curve. T is an additional parameter that we put into x and y to produce points on the curve. All right, you guys. I hope that was entertaining. It's pretty easy. Calculus with parametrics is pretty simple. So thanks for your time and attention. I look forward to seeing you tomorrow. Have a good day.